So if we look at the rotation, we know we have to deal with the summation of moments equal to 0 equation. 0 is because we assume static. All right? So over here, I'm gonna have to go to the page from last time. Let me just redo a figure, might be just easier. This problem instead of going back and forth. All right, so if I take our cut, I'm just going to redo the figure of our cut over here. We had the distributed load. And then we had the shear forces, V1, V2. We said they go in opposite direction because the system needs to be in equilibrium, no? Same thing for the moments, M1 and M2. And here what we're going to do is that, so this is position X1, X2, and the point about which we're going to take the moments is about, let's say, the center line, okay, of this element. Okay, so if we take moments about the center line, and we assume the moments to be positive counterclockwise, this is the normal sign convention. If you want to change it, you can change it, but you need to let me know. If you don't put anything, I'm always going to assume the normal sign convention for the moments, okay? Equal to 0. So over here, what do we have? Minus M1, because it goes clockwise, plus M2. Now, plus V1 of x of 0 minus x of 1. Down will go counterclockwise, no? And then this one will also go counterclockwise, plus V2 of x of 2 minus x of O. I should leave some more space over here. Now we need to assume what's going to happen with the distributed load. So minus Q of x, let's say, would be x minus x of O dx. Okay, and this will be between x of 1 and x of 2. This should be equal to 0. Okay, same as before. I'm going to rewrite this moment a little bit differently. It's going to be the same thing, but instead of writing M2, I'm going to say this is the moment at point 2, at x2. And this would be the moment at x1. So really, this is M2 and M1 plus V2 x2 minus x of 0. Now be careful here because I'm going to reverse the sign for V1. So V1, instead of having x of naught minus x of 1, I'm going to have x of 1 minus x of naught. Okay? That's why I'm reversing the sign. And now again, I run out of space for that one, minus the integral of between x1 and x2 of q of x, x minus x of naught dx equal to 0. Okay, so as before, let me just do an extra step. So these two terms over here becomes what? Integral of dm dx times dx between x1 and x2. So this comes from these two terms. This is the definition of the integral, no? The integral of this is m2 minus x1. Okay, that would be the definition. All right. Now I can do the same thing for this one over here. So this will be plus integral x1 x2 of dv dx of x minus x of 0 dx. Oh, I should have done a middle step. Okay. I thought I was going to do a middle step and okay, I think I can still do it. Minus integral of x1 x2 q of x minus x sub naught dx equal to 0. Okay, so I'm just going to write the same line over here on the next page, except that this time I'm going to write it a bit differently, okay? Page 91. See if I can put everything in one line. So we're going to have dm dx between x1 x2 plus, this is the term I'm going to write it a bit differently, x1 x2, because that's the way I should have written before, of dx of v dot x minus x sub naught, and this should be now dx minus q of x minus x sub naught dx equals 0. Okay, so remember, all this comes from the moment equation. So what is the definition of moment? Force times r, no? Okay, so this is two different, this is not v at x minus x sub naught. This is force times this, okay? All right. So this means that we're gonna get over here dm dx. And now from this one, we're gonna get plus, this one is gonna give two terms. So the first term will be dv dx is like doing uv is u prime v plus uv prime. So it would be dv dx times x minus x sub naught dx plus v ddx of x minus x sub naught dx, and the last one will stay unchanged. Equal to 0. So basically this term over here give these two terms. And from the first derivation, we had that dv dx is equal to q of x, okay? So we know that this term over here is Q of X. So what you're going to see is that this term is going to cancel this one. Basically, that is what's happening, no? Okay. The second term is going to cancel the last term. So here we're going to get at the end that you're going to have dm dx plus integral of v. Okay. Okay, I do it this way. I explain it quick instead of doing it. Would be v dx, because what is x sub naught? X sub naught is a constant value. Okay, so we take the derivative of a constant value, we just end up with dx, and this will be equal to, so these terms cancel this one, so this will be equal to 0. And I'm just going to add now again the limits of integrations, which are not really needed, but it's fine. So now we can combine. If you remember the derivation, what was it? We derived the equation. We went from a surface integral to a volume, and then you need to put the same type of integrals, no? So here we have the same type of integrals, so we can combine them between x1 and x2. So we're going to have here dm dx plus v dx equal to 0. Okay, so we can say that the above equation is satisfied if dm dx plus v equal to 0, or which is the same thing, v equal to minus dm dx. Okay, so remember all this was to define, the other day we went through the general procedure of how to derive the equation of motion. Okay, but this time this is the equation of static motion, no? This is the static equation this is the static equation. You cannot call it motion because it's not moving. And we went through the process, all right? And this is the same step, but a lot simplified, no? Okay, so imagine to have to do this stuff in 2 or 3D. Okay, so the summary of this problem is just like, what do we have? We have that the distributed load, see I can put it on the screen, is dv dx, and that you can get the shear minus dm dx. Okay, and these are the classic beam equations. From really, you should have derived this in statics and solids. Okay, personally, I know that was a long time ago for you, no statics. But if you ask me what is the most difficult part in statics, is this: how to do those shear and bending moment diagrams. Yeah, so I don't like the way to do it. If you have a straight line, it becomes a quadratic. No, really what you have to do, if you know the distributed load, you needed to integrate, no, in order to find the V. And once you knew the V, you needed to integrate the shear force in order to find the shear distribution for the moment. That was really the way to do it. Okay, and then we integrate, and depending on the boundary conditions, so by integration you end up with some constant of integration, and then you solve the constant of integration depending on the boundary conditions of your beam. In this case, it's simply supported, no? Yeah, so we're not going to do it, but what would be the boundary condition that you could use over here, for example, if you needed to solve for the moment? what would be the deformation at this point? The vertical deformation is 0. You could use done, those two conditions, or you could use what? What would be the moments at A and B? At the two ends, what would be the moment? Moments would be 0 because it's free to rotate, no? But if it was clamped, then it's not 0 anymore. Yeah? Okay. Okay. Okay, so now before we start the next section or chapter, let me tell you why we do this, okay? So for example, if you needed to summarize your classes about solid mechanics. What are the two equations you use all the time? Basically, you needed one equation that will define the forces, and the forces are always modeled as vectors, correct? So the equation you will get the forces or the moments will be summation of forces equals to MA, Newton's equation, and then you could do summation of moments. But now in solid mechanics, you need to be able to relate the forces to the material, okay? Because if you apply the force to a piece of wood, it's not going to be the same as if you apply it to a beam made of steel. So what is that equation that will help us to relate the forces to the material? It was one equation, which is called the stresses is equal to the Young modulus times the strain. This is just for bending. You have one similar for shear. Okay? So this is the equation. And why can you relate this one? Because you know that the stress is force over area. No? So you will calculate the forces from here, and then you can calculate the deformation that are given by epsilon, by the strain, through this equation, which is Hooke's law. All right? In fluid mechanics, basically you have the same thing, but here is, if you do statics fluid, is summation of force equal to 0. If you do real Navier-Stokes, you end up summation of force equals to MA. So you calculate all the forces that are given on the fluid. And now, what is the equation that relates the forces to the type of different fluids that you have? What is the main assumption you do all the time in fluids? What happened at the surface? No slip condition. No slip condition means no shear, correct? Remember, you generally do that figure over here, like no slip condition, no? And you put here what? V equal to 0 basically means tau equal to 0, no? No shear. So what is that equation that you use all the time? Generally, you use the dynamic viscosity, and then you have generally dV, I don't know how you call this one, you call this, will be times the velocity profile. Yeah? But basically, both of them are summation of forces at the beginning, and then you need an additional equation that relates whatever problem you're solving to the type of medium. So here, if it's solid, the medium is solid, you use Hooke's law or modify Hooke's law. If it's fluid, you end up with the shear equation. Okay? But you see, both classes are basically the same thing. So what is the name of this type of equations over here? This type of equations are called constitutive equations. All right? This one over here and this one over here. So what we're going to do next is the constitutive equation, derive the constitutive equations. All right? So if you want, this is, I have here as chapter 3, but since I'm changing the order, let's just say here, let's just call this one constitutive equations. And by the way, I mean, you're not going to benefit, but I think I was looking the other day at the notes of maybe of the last 2-3 classes. I think my indexes are a mess. So I think I'm going to go back and try to rework all the indexes consistently, okay? because it's hard to follow now with the indexes they have because they change almost in every single equation. Okay, so the constitutive equation. So let's look at the mathematical concept. All right, so here, this is more into detail, okay? We're going to talk about the material derivative computes the time rate of change of any quantity, all right? Velocity, temperature, whatever you want. Moving with a velocity v. Okay, there are other names for the material derivative. Some people call it the substantial derivative. They also call it the total derivative. They call it the convective derivative, but I like to call it the material derivative, okay? All right, so the expression for the equation is d, and that's why they call it full derivative or substantial derivative. You have d dt of whatever property or quantity you try to define is equal to what? Is partial of partial t of your quantity plus v partial of the quantity partial x. Okay? So leave one space over here, and then I'm going to write the same equation here. Oops, don't put x here. It should be empty. Sorry, it should be empty space and this. So over here, basically, we go to a fundamental problem, but that is extremely important, okay, for the understanding of the derivations of the equations and to understand the main difference between solids and fluids, okay? So the first one over here, imagine, I always kind of give the same example. Let's say you look at something that is at the back of the pickup and you are looking at it, okay? From the outside, you see a pickup and you see something at the back of the pickup. And you want to describe the motion of whatever is on top of the pickup. So the object is moving along the pickup, no? So if you want to write the equation in function, if you are on top of the pickup, you need to put into consideration that you are moving with the object, correct? So you can derive the equation of motion. You can derive all the equations. Now, it will be different if you want to derive the equation. Let's say you are an observer, which is outside. You are on the street and you see whatever is behind the pickup truck moving. You can also describe the motion of that object, no? Okay? But in both cases, the reference system is different, okay? So that's what one they call the Eulerian reference frame, and the one they call it the Lagrangian, okay? So if you are moving with a pickup truck, is the one that they call the Eulerian reference frame. And that's the one you use mostly in fluids, okay? So this is here so this one here is Eulerian reference frame. And then if you are not moving with the object, what does that mean? this term here is 0. So you see the only difference between this one is that this one you need to add this term, and this one you only have the traditional derivative, no? But if you are on the Lagrangian, you need to add this term, and that's why they call it the convective also derivative, because you need to add this term which is showing the movement, no? Okay? And this one would be the Lagrangian's reference frame. Okay? But if you use one or the other, you should end up with the same, at the end, with the same result, no? Otherwise, it will be a problem, no? If your result depends on the reference frame. So again, this is a complicated concept, but I'm going to take a very simple example, okay, to show it. So again, this is extremely important conceptually. If you ask me, I used to ask sometimes, like, I mean, once I asked for a qualifying exam to a student, was like, explain the difference between the full derivative, let's say about the normal derivative and the material derivative. That was the whole question. So basically what I need to do is write this down and show that if you have this term was the Eulerian, this one was the Lagrangian, no? Nobody did that question. So I don't put it anymore. No more conceptual questions. But I think it's an important question. Okay, from the conceptual point of view is you need to know on which reference frame you are deriving your equations, no? And that's basically the only difference between solids and fluids. All the rest is on page 93. Okay. All right, so let's do it's a basic example, but I mean, if we do one complicated, just too long. So, example. So consider a ball being thrown straight up, okay, into the air. I don't think that's important, but and we need to determine the acceleration of the ball using A, the Lagrangian reference frame, and part 2, the Eulerian reference frame. So the same problem of this one would be, for example, what happens if you throw, let's say, a metal ball into a bucket full of oil? Would be kind of the similar, no? But it would be more related to fluids than this one that is more dynamic. That could be a question, you see? So again, we can have this one. So if I do a little sketch, remember always the procedure in fluid, statics, dynamics is that you get the equation from a figure, no? Okay? So in this case, let's say you throw it up. So you have your ball over here. You know the velocity, V naught. And this ball will also be subjected to the gravitational force. All right. So let's say over here, then you also need to define always a reference frame. So let's say here we choose this reference frame as Y. And let's say initially, I mean, you could put this as 0, but let's say it's at a constant y sub naught. Okay? So this is the classic way, okay? This is dynamics 100%. So from kinematics, I mean, this is not that important, but now that you go to PhDs, you need to start maybe see what is the difference. What is the difference between the terms kinematics and kinetics? See, it sounds kind of the same, no? So kinematics means that you derive the equation of motion just by using in either one of these two equations here, A equals dv dt of V equal to dr dt, where this is the position vector. Kinetics is the same thing as dynamics, means the same thing. Is that you can derive the motion from where? From summation of force equals to ma. You can solve for A, no? Yeah? But here you don't need to know any force in order to solve. So this is kinematics. The other one is what is called dynamics or kinetics. Okay? Anyway, so here we use kinematics. So from kinematics, do I do the whole derivation or? Okay, let's maybe do the whole derivation, okay? Well, then plan do it. Okay, so if you look at it, what is the gravitational force here? It's 0 minus g. Okay, now if you want to find the velocities, there is no velocities on the x, no? And in order to go from velocities, if you know the integral and you want to find the velocity, what you need to do, you need to integrate. Okay, so what do you get on this one? So you get here minus gt, the integral of g, plus the initial velocity v sub naught. Okay, and now you want to go from this one to the position vector that basically is xy. In this case, what are you going to have? You're going to have still 0 over here, and now you need to integrate this one. Okay, so if we start from this one, you will have minus gt squared over 2 plus v naught of t plus y sub naught. I mean, this is physics PS 150, whatever physics, dynamics, no, basic stuff. But you integrate, so here you integrate because you follow these two equations. Okay? Okay, so this is, let's say, part A. So basically over here, the only thing I'm trying to show is that I mean, it's going to be redundant, but the only thing I'm trying to show is that if you have V equal to minus GT plus V sub naught, I mean, we did the integral, what would be dV dt will be equal to the acceleration, which will be equal to negative G, no? This is just the result that we need to find. Okay, so since I'm doing this derivation, maybe I keep going doing the derivations or not. Okay, let me keep doing work, okay? So what are the two equations we have here? This is not really needed for this problem, but at least you can see what is the procedure generally to follow. If you have these two equations here, and let's say you want to eliminate the time, what could you do? You can use the chain rule, but another way to do is to do dt here will be equal to what? dv over a, and this will also be equal to dr over v. Okay, so now this is a differential equation that you only need to do in order to solve a differential equation, the first thing you need to do is separate the variables. Correct? But the variables are together, they are the same together. So it will be, so you have v dv will be equal to a dr. Okay? Now you can integrate, let's say between v1, do v1, v2, or between v initial and v. So we use the same notation on here. This is the v initial, then plus v. And this will be, let's say, y sub naught and y. So what would you get from this equation? You get v square over 2 minus v initial square over 2 would be equal to a times y minus y sub naught. Okay, so from here you can get that v square is equal to v naught square plus 2. A here is equal to negative g. Yeah, the acceleration is going down, no? This is going up, this is going down, no? So, I mean, it makes sense. If you throw it up, it's going to slow down, no? Due to the gravitational force. So it will be minus here, you can put it right, minus 2g of y minus y sub naught. Or I mean, you see, one problem was very quick in the Lagrangian. Now with the Eulerian, it's a little bit more work, no? Or you can just rewrite that equation, or v would just be equal to v naught square minus 2g y minus y sub naught, and this is the square root of all this. So why are we doing all that stuff? We're trying to solve with the material derivative, no? Okay, so we say Eulerian, we need to use the material derivative, which is what? dt of a quantity. So here, what is the quantity we're trying to study over here? The velocity is equal to what? Is equal to the partial derivative of the quantity we're trying to study with respect to t plus v, the velocity, partial of the quantity we're trying to study, which is v, with respect to y. Okay, that's the definition. Okay, so, and the expression for v, we have it right over here. Let me check one thing here. Let me check the way I did the equation. Yeah, this is correct, okay? So over here, is this function in function of t? Just look at it. Is this in function of t? No, okay? So this basically will be then 0, okay? And now, so we have here either plus or minus because it's a v squared. Okay, okay. So what will be the derivative of this? What is v? Okay, sorry, here is plus or minus. Okay, so is v, so it will be plus or minus of this whole quantity over here. I don't know how to write this. So v0 squared minus 2g y minus y sub naught. So this is v. Now we need to do the partial v with respect to y. So what is the derivative of this? Remember how to do this would be, it's like doing x, derivative of x to 1/2 will be 1/2 of x to 1/2 minus 1, no? With 1/2 of x or minus 1, okay? So this will give you what? We'll do here 1, this, and then you have over here plus minus, and then the term will be the derivative with function to y will be 2g. Is the only one in function of y, no? And then basically at the bottom, you're going to have the same term. Is the 1/2. Now the 1/2 over here, and then should be the same expression here. So v naught squared minus 2g y minus y sub naught. Again, all this term over here is v partial y. Okay, so if you look at this, this will give you what? These two cancel with these two, and all this term over here is going to cancel with this term over here, no? All this square root is the same as this one, no? Identical. So we are left over with what? No, the 2 cancels out with this one. So we're just left over plus either plus or minus g, no? But actually it will be, should be minus g, because you want, if you have the plus here, you will have the minus over here, no? So it's only minus g. Because of the derivative, one should be plus minus, the one will be minus plus. Okay? So you end up with minus g. So what was the conclusion that we had before? If you look at the page we had before, is that we concluded that the A, which is dv dt, okay? So A equals dv dt is equal to minus j as before, as expected. But you see that before, I mean, you see that this one is a lot more work, no? But if you have fluids, actually it's the other way around. If you try to do it the other way, it's a lot more work than this way. Okay. So we're going to look at the initial notation for the material derivative. Okay, so we know the equation is d dt of whatever quantity will be partial of the quantity with respect to t plus the velocity, whatever the quantity with respect to whatever dimensions is moving. Okay, so as an example, it will be easier. So as an example, let us consider the quantity temperature. Okay, it's a property. Okay. So we write d dt of the temperature will be equal to partial of t of the temperature with respect to time plus velocity partial of t with respect to the x, y, and z, no? Okay, but let's say the general will be this one. So if we needed to expand this equation, not in initial notation, but on the that would be equal to what? So we're over here. Material derivative for the temperature will be equal to what? Will be the temperature change with respect to time plus now the temperature change with respect to the three different in space, no? Okay? So the temperature does not have to change at the same velocity on the x, y, and z. So you could have Vx partial t partial x plus Vy partial t partial y plus Vz partial t partial z. Okay? Or now we read this in digital notation will be d dt of partial t with respect to t plus, you know, x, y, and z you can replace by 1, 2, 3 of partial t partial x of I, which is the way I will write it, okay? But if you want to be even more reduced on the notation, you could write this as t comma t. I don't like this notation. I think it's too much, no? Plus v of I times t of comma I, no? But I don't like it. I will stick with the first one, no? I think this one is a good compromise between writing everything and be more clear. When you start putting this, I lose a little bit what's going on. Okay, so why is this equation important? It's important for many things, but now if you go to type of fluid, what is one equation that derives all the time in fluid is the conservation of mass continuity equation, no? Okay, so what time is it? We have 20 minutes, no? So let's get started. So next thing we're going to derive is the continuity equation. But what I like to call, because I think it's more significant, the conservation of mass equation. So now, why is this important? It's because the, and you will see why, but the continuity equation enforces the conservation of mass, but this is the important part, in an Eulerian system. So continuity equation, you use it in fluids, no? All right. And I'm sure you have derived that equation at least 3 or 4 times. I know you also derived it in 501. Is anyone taking 501 this semester? Are you taking 501? With Eduardo, with Divo. Okay, so you have done this for sure. Okay, so this is a classic figure where you have, so I don't know if I want to do a lot of detail, but is the one that you consider a control volume element. Okay, you have a big volume, you take a control volume. You have this. And then let's say you have here the reference frame X1, X2, X3. That's where the figure can become very messy now. So let's say if you go at the bottom, let's say at the bottom you have a quantity of mass rho V2. Remember, this is the mass because density is mass over volume. Okay? If you take a volume element, the mass becomes the density. Yeah? Okay. Now, so if center mass comes over here, what should be the amount of substance coming out of this side? Would be the same quantity plus partial of rho V2 on the X2 direction, dx2. I'm sure you have done this one, no? In this one would be rho V1, and what we'll be leaving over here would be rho V1 plus partial of rho V1 partial X1 dx1. And then the one is going to be complicated is this one over here. So on the back over here would be rho V3. The front would be rho V3 plus partial X3 of rho V3 dx3. Okay, so remember this is your control volume. This is a volume, okay? Volume element. So now if you apply, same as before, you do your, instead of using summation of force equals to MA, we're going to write it as the momentum equation, no? But the mass becomes rho, no? For the volume element. So we apply this equation to the volume element. So what do we have? Whatever is coming in over here, no? Into each one of the faces, what do you have? Rho V1 is coming in which phase? dx2, dx3. Yeah, it's coming on this phase, which is dx2, dx3. So dx2, dx3. Now, plus rho v2, that is coming in which phase? dx1, dx3. Plus rho v3, that will be dx1, dx2. Okay? And now basically we're gonna have the same thing with the ones coming out, but will be a negative sign because one is coming in, the other one is coming out. So it will be minus, so what? Rho v1 plus partial x1 of rho v1 dx1 dx2 dx3. Okay, I'll do it this way because it's going to be less confusing for me. Minus rho v2 plus partial x2 rho v2 dx2 dx1 dx3. And here, maybe I do it now, you see what's going to happen. This term over here is going to cancel this one. This one's going to cancel this one. And this one is going to cancel the one we write down next, okay? So 96 minus rho v3 plus partial x3 rho v3 dx3 dx1 dx2, and this is equal to the partial t. Remember we have mass, but now we have the density dx1 dx2 dx3 because we apply it to the volume element. Okay, so really, this would be equal to what? We simplify, we're gonna have rho x1, rho v1, plus rho x2, rho v2, plus rho partial derivative of x3, rho v3, dx1, dx2, dx3 will be equal to partial t of rho dx1 dx2 dx3. And actually I should put here a minus sign, sorry, because it should be a minus sign here outside. Forgot the minus sign. Let me just rewrite it. That way it will be just easier. So we'll get minus partial x1 rho v1 minus partial x2 rho v2 minus partial x3 rho v3 partial t of the density. Or we can write this as partial of this. So this would be the same term. Let's say we see what is the material derivative of the property density. This would be the first term, no? Okay. Now we need to look at what happened with the other terms here. So it will be plus partial x1 rho v1 plus partial x2 rho v2 plus partial x3 rho V3 equal to 0. Or we can rewrite that equation as what? Partial of density partial T plus, what is this? When you take the partial derivative of each one of them, this is the gradient, okay, of what? Of rho V, the vector, okay? And this is equal to 0. So this is the continuity equation that we can rewrite as, if you want to use some initial notation, should be equal to what? I will rewrite it under this form, partial of x sub I of rho Vi, but I will not go to the other one, okay? I'm not even going to write it down. So either one or this one here under this form in initial notation. And this is what is known as the continuity equation. Okay, and we do that next time, but in here, generally, you have two assumptions. So what happens, generally, you assume, to simplify the problems in fluid, you assume two things. One is that it's steady state. So if it's steady state, what does that mean? The density does not change in function of time. But now, if somebody asks you, what is the definition of an incompressible fluid? So you will have what? We have the del of rho V will be equal to 0, no? But if it's incompressible, what does that mean? Density won't change position. Okay. So basically it means that if it's incompressible, the density is constant because you need that to be equal to 0. So one definition, I mean, mathematically is correct. Conceptually, I don't think it's a good definition, no? But mathematically, if somebody asks you how will you define an incompressible fluid, from the equation will be a fluid for which the density is constant, okay? Mathematically, it's 100% correct. Conceptually, I'm not 100%. I think there's a lot more involved than the density, okay? It has to do that the properties of the density are conservative, no? Basically, if you take E501, you have conservative fields and non-conservative fields, no? Displacement fields. Basically, it means that the displacement field of the density is conservative, and that's why it's incompressible, okay? But I mean, again, mathematically to say that is constant is correct. Okay, so we stop over here for today.